How many of you here are statistics savvy? What's that? Define statistics savvy. So, have you taken some basic statistics of
Just
intro? All so you're all comfortable with hypothesis testing and all those null distribution, categorical data analysis like logistic regression and stuff like that. Okay, so then in that case, this lecture is going to be basics in the sense that we are going to deal with very basics of data analysis, statistical data analysis and modeling. Okay, but next topic which we are going to cover on Thursday, it's going to be a little advanced in the sense that we are going to deal with maximum likelihood and some optimization principles behind it. Okay, so it's more, but then I have made a point to make it more practical and not deal with theory by taking an example and working out how these things really work in general. Okay, principles behind. Are you all familiar with linear regression? What assumptions that go when you try to fit the model? Okay. All right. So yeah, so that's going to be today's topic. We will be going through some basic inference and linear regression. All right. All right. So this is going to be the same. We are going to take our Haynes data set. It's my favorite data set because there are so many numerical variables in there compared to the mimic. You have one data table which is, I think, the input CV that has numerical, but then you can always construct numerical like making a count of some variable, right? So you can, or some kind of a you can gather some variables and make your own new categories, right? So some of these things we can do, but Haynes is good in the sense that there are, I think, already at least 16 variables that are numerical in there. Some are blood measurements and some are urine measurements. So we already have a nice good amount of numerical continuous data in there. Okay, so we will take this data set, and what I'm trying to do here is one of the key things that I'm adding here is a set seed thing, which is important because of reproducibility. Otherwise, every time I run and compile this code, I'm going to get new results, and I don't want that. So I'm trying to set the seed so that it's consistent across my iterations. Okay, that's it. I mean, we have the basic data set here, and we are going to install a package called Raphaelib. Okay, this is from MIT or Stanford, I'm not sure, but they have a very good course in basic R, and probably they also have, it's called, I think, stats for 545 or something like that, and they have some machine learning algorithms on that as well. But this is kind of different course, so we are taking some bits and pieces in there. So we need a package, so we will install that package and load that library in here. Okay, z-test. What is a z-test? Anybody knows z-test? Recalls z-test? I mean, it's a simple test in the sense that if you know all the parameters, right? I mean, from the central limit theorem, if v and z are two IIDs, or independent and identically distributed random variables, and nu v and nu z are two the means of them, and we have the standard deviation, then this ratio approaches the normal distribution centered at 0 with standard deviation 1 as n becomes large, right? So it doesn't matter the original distribution has to be a normal distribution or anything. It is regardless of what distribution the data comes from, this result is going to be true, right? But in general, we will not know the mean and standard deviation of a population, right? I mean, this is the central statistical inference problem, that you have a population, but we don't know what the original population is. We only have a random sample from the population. And so in particular, if these two are normally distributed, then we can see that the ratio which is given by this approximation is also normally distributed. And so we can use the p-values simply because we know the proportion of the distribution under any value. This is straightforward normal distribution, so we can find the p-values. So for instance, only 7% of these values are larger than 1.8 in absolute value. So we take since the normal distribution is symmetric, so we can look at the area which denotes the probability, and we can see that only 7% of the values are larger than 1.8, right? So thus, if we know the original population is normally distributed, the standard deviation of the population, and if the sample size is large, we can use this approximation, right, to get a p-value. And this is the known famous z-test. But there are so many conditions here. The first is that the population being normally distributed, in practice we may not really know whether the population is normally distributed, right? I mean, but then we can try to take the random sample and see how close it is to normal distribution, and that can be done by using QQ plots. Have you used QQ plots before? Right, the normal plots, right? I mean, this is to confirm if the distributions are relatively close to normal. So what we so in our example, right, we take the hemoglobin variable A1C, and we will consider people without diabetes as control group and people with diabetes as the disease group, right? And we try to plot to see how far they are normally distributed. So we have the control. I'm filtering here, and I'm taking people with no diabetes and then selecting only the variable that's of importance, which is the hemoglobin content, right? And then I'm trying to see if things are okay, and it's fine. I have those values here. Now I can try to make a QQ plot of the control variable. So we have the control variable, and I'm trying to get the quantiles of those control variables, and then we can plot the control variable with respect to those quantiles, right? So once we have it, we will see that it is almost here. It's kind of following the line, right? The line stands for the normal theoretical versus the sample distribution, and you see that it's really following that, right, for the control variable. And similarly, we can make a QQ plot for the disease variable. So I'm taking the quantile of the disease and then I'm trying to plot it with a slope, right, just to get a line. If you do that, it's okay. I mean, it's you may not want to call it as normal, but it's kind of okay. So it's more, the control variable is more normal than the disease variable, right? Thus a z-test may not be really appropriate even if it is normally distributed. The major disadvantage of using a z-test is that it requires the standard deviation of the population, right, not from the sample. So for a z-test we need to know the standard deviation, and that is where another kind of test comes into play, right? So this is a homework. Check the glucose values for normal for the non-diabetic male and female population are close to normal. Okay, so this is a simple thing that we can do. So that's where the t-test come in. Even though we don't know the population standard deviation, we can estimate from the sample standard deviation, right? So we can take a sample and then try to form this standard deviation, and there is this n-1 because there is an approximation here. It's not n, and there is a mathematical reason behind it, but now we can take it just as the formulas, because the point of the course is to see how these things really apply to the data and not go into theory too much, okay? And so we can calculate this value, the ratio, with this sample standard deviations that we approximated. And this has to be approximately normal, okay? So this is called the t statistics, and the distribution is called the student's t distribution, okay? So this is what we are going to do, and we are going to take this t statistics. Okay, so here, although the disease variable in our case is not really normally distributed, and let's assume that if it's normally distributed, we can apply the t-test to find the p-value here, right? So the t-test in R is just t.test with the disease and control, and it's going to do a Welch two-sample t-test. And there are variations of this t-test. When you have a paired sample, when you have an unpaired sample, there are so many other conditions and things that could be incorporated. Okay, so but this is just a very simple basic t-test, and it gives you a p-value of really a small. So we can try to do this for male and female populations and see if it is of significance, right? P-values are everywhere in life sciences, right? I mean, it's everywhere, but it's not good to rely on p-values, right? Why is that? Why p-values are really bad? There was a recent Nature article that was criticizing scientists using these p-values as a. I mean, it's crazy because it doesn't really give you anything actually. Correlations are not causations, and there are so many other things that are to establish causality. It's not just based on p-value, right? It's just that it's one single number, and that really doesn't reflect what it means, right? So all it says is that the chance of observing a value away from the mean is small, in the sense that so that the null hypothesis can be rejected, right? So a better alternative is to report the confidence interval, and I would actually harp on this aspect of it, because when you when you report the confidence interval, we don't infer any significance, or I mean, we don't, although it means some significance, it doesn't really uh, import the value that we associate with the p-values. Okay, so it's better to report a confidence interval, and confidence interval include information about the uncertainty associated with the estimate, right? And that's important. So a 95% confidence interval is a random interval. It's also a random variable with a 95% probability of falling on the parameter that we are estimating, right? So we can construct it easily. So the central limit theorem is that this ratio, right, square root of n, the mean, the difference in their mean by standard deviation should follow a normal distribution, right? And so we can easily construct this interval around which the difference in the mean follows, right? I mean, this has to be around 95%, right? So with this, we can make some basic algebra and then see what is the chance of the mean falling in between these two intervals, right? So that's the basic idea behind confidence interval. And so in our case, we can estimate that. So what we are going to do is that we are just applying this formula here. Start taking the standard deviation, and then taking the confidence in the interval from the normal distribution, and then trying to estimate whether the mean between the disease falls between these two intervals, right? And so it's true. So it gives you an estimate of the confidence interval here. Now we can do the same for the glucose variable, right? So that's a homework for you to do. All right. So, but in general, if you think about all these tests, all the hypothesis tests, that so far it's between continuous variables. You have some values which are nominal, right? But in general, there are so many problems that come with a categorical, binary, and other ordinal variables. And so association tests are very, very important, right? For instance, a genome, right? It will have a mutation or not. It's a binary variable here. And in general, association tests are really important for determining whether there is an association that we can establish from the category. So let's look at a mimic3 admissions table here. For example, we have I'm taking the admissions table, just reading from the from the database. And let's say that we want to find the odds of finding separated. So if you look at some of the variables in here, right? So there is a variable called the ethnicity here, and also there is a variable of insurance here, right? So I just wanted to see the odds of finding separated black people with Medicaid are almost the same as the ones with government insurance. Okay, so this is one of the tests that I wanted to see with this data. And so to do this, we first need to find the number of people who are separated and have Medicaid and government insurance and find their ethnicity. Okay, so that's what we are doing here. I'm trying to find the insurance and marital status. From this data, I'm grouping by insurance and marital status and counting the number of people. Okay, and I have the folks with Medicaid that is taking and then filtering for insurance equal to Medicaid and counting it. And I want to find also the number of people with Medicaid insurance and who are separated, right? And also I want the ethnicity. So these are the 4 things that I need from this data, right? So with this, I get this group of insurance and marital status, if you list it as a table, you have the government and the Medicaid and so many other people with so many other insurance schemes, and also the people's status, marital status, whether they're divorced or married or separated, etc., etc. And from here, you also see the number of people from here, right? And that there are 622 of these groups. And also I'm trying to do the ethnicity as well as so for this one, right? So when I have the Medicaid and marital status, and I'm listing out these people as well as with the government insurance and separated, right? I have these 4 data sets, and we have this the ethnicity, and then this is the government insurance, right? Now, in particular, the question that we ask about the data is the following. Knowing the 3 out of 5, right? There are 3 people here, right? And there are 2 of them in the government insurance, right? So there are 3 out of 5 separated blacks have Medicaid insurance, right? And 2 out of 5 have government insurance. Can we reject the null hypothesis that the odds of finding separated black people with Medicaid is same as the odds of finding with the government insurance? So what do you do for such questions when you want to find an association? You build a contingency table, right? So that's what I'm trying to do here. All these analysis is just to make a contingency table, and that can be answered using Fisher's exact test. Okay, so Fisher's exact test applies to the small population, small sample size. So if you look at here, you don't have really large groups here, 3, 1, 2, 1. I mean, these are small numbers. So Fisher's exact test can be used to compute the reject the null hypothesis or accept the null hypothesis, right? So we have, based on this, we can form this contingency table with how many people you have the Medicaid 3 and non-black people with 9 and the government with 2 and 1, right? And we can perform the Fisher's exact test, and so you immediately get the p-value of how much? It's 0.24, right? So it suggests that the null hypothesis holds. And so the odds of finding separated black people with Medicaid are almost the same with the government insurance. So you cannot really reject them. So how to construct and it's also important when you want to apply Fisher's test, right? You have to make sure that the sample sizes are small to make meaningful inference out of it. So that's why it's, in general, Fisher's exact test is much more, for larger samples, it's better to use chi-square test instead of Fisher's exact test because it gives a good approximation. So in the above example, we have the sample size of 15, right? And overall, if you look at the number, right, 3, 9, 2, and 1, it's 15. But if we have a large sample size, chi-square test gives a good approximation for the confidence interval, right? So let's use the chi-square test to see if there is an association between ethnicity and diagnosis of a disease. Okay, so we consider 2 ethnicities here, white and black, and the diagnosis of a disease called diabetic ketoacidosis. Okay, so this disease, right? I was trying to see what in general is the diagnosis information that's there in this mimic admissions data. And what I did was here find the diagnosis and ethnicity info by grouping these variables, right? And when you list the diagnosis ethnicity, we see this. We see that there are so many diagnosed diseases, and especially one of them, right? Black and African American population, it is 33. Whereas for white, this particular diagnosis is 18. Okay, so we can just test this hypothesis of whether the total count of 510 people, this is the number of black population in there, and there are nearly 4,000 of them are unaffected by the disease, right? Now with this, we can form this contingency table and ask the question of whether this disease is associated with black people more than the white people, right? So this is the black, this is the unaffected population 510 out of the total population. If you look at it, it is 543, right? Out of them, 33 have the disease, and here 4,000, and out of which 18 of them don't have the disease, right? So you form this contingency table and perform a chi-square test. So immediately we see that there is a good association, and so I looked into that, and in fact I went to some literature, and in fact I saw that this disease is common among Black and Hispanic population. So it's it's a pretty neat information that we have such an association obtained through this mimic data set. Okay, so I'm not sure if this is reported or something, but I mean, so many questions, even within one data set, right? You can ask so many questions. You can gather the variables in different ways, you can club them, and I mean, it's endless actually. And so, as a homework, perform chi-square test and report the association between the variables of choice in your favorite data set. It doesn't have to be, I'm not specifying any data set. You can take an example and then try to construct the contingency table, okay? So one of the key assumptions on some of these tests is that the data has to be normally distributed, and it may be too much of an imposition to run these tests, right? So in that cases, there is another test called Wilcoxon signed rank test. It can be an alternative to t-test. So it's a non-parametric method in the sense that there are no rigorous parameters like mean or standard deviation that can be used to test, but it's based on what is known as ranking, right? So the basic idea is to combine all the data, turn the values into ranks, okay, and then separate them back into their groups, and then we compute the sum or average rank and perform a test. So the sum is performed on the rank, and that is why even if you slightly change some values, these Wilcoxon signed rank test will give you almost, the p-value will not change or the confidence interval will not change, unlike let's say the t-test, right? If you change the values, there is a good chance that the confidence interval gets changed, because here you are just assigning ranks to it, right? So you are putting it in a bin, right? And in our Wilcoxon test, there are so many tests available here, and this can be used to perform. And we are performing this test on the urine mercury levels in the diabetic and non-diabetic population, and we see that it's almost it's 0.09, so we may not really see any big association in there, okay? So as a homework, perform the Wilcoxon signed rank test on any two age groups. There are three age groups in there for this cholesterol variable. Do you see any significant difference? You have to answer that. And there are other tests to check if a sample or a variable is drawn from a normal distribution, right? One of them we saw at a QQ plot. But other than that, there are some tests that we can do. Shapiro's test can be used to test, if a variable is drawn from a normal distribution. So it's a very simple test. We check the triglyceride variable, and we take the triglyceride variable and then do this test, and it says that it is significant, right? I mean, if you look at the plot, right, some of these plots we can say that some of these values could be normally distributed because it will be centered around some mean, right? I mean, for most people. So the extreme p-value suggests that a triglyceride variable has indeed a normal distribution. And there is another test called Kolmogorov and Smirnov test that can be used to see if there are two variables that are drawn from the same distribution, right? So here I'm trying to take the triglyceride and cotinine variables and then trying to apply this test, right? And then it gives me a significant p-value, right? So the results suggest that they are drawn from the same distribution, and we already know that triglyceride is drawn from a normal distribution, so cotinine should be drawn from it as well, right? So you can perform these tests on on 3 different variable pairs in the Haynes data set. Okay. Correlation test for linear relationship between the variables, right? The famous Pearson correlation. So COR test computes the correlation between two continuous variables, right? The null hypothesis is that there is no correlation between the variables, and we saw in the data analysis earlier that LDL estimate and cholesterol total seem to have a linear relationship. Do you remember those? Kind of saw that, and so we will verify that here. Okay, so what we are doing here is selecting the LDL estimate and cholesterol total and trying to perform a correlation test on these variables. Okay, so there is a very significant association with that. Okay, so this is good. And then we will try to figure out how these two are really related. Okay, so we see that there is high degree of correlation, and that's
One question. I mean,
yes.
for this correlation analysis, the correlation coefficients and the p-value, which one is more important?
Oh, well, they are related, right? If there is a good amount of correlation, the p-value is going to be low, meaning that there is going to be, yes. What you are trying to ask is a more complicated question. In general, whether the linear regression is a good model for the data. We will, we will answer that question later. But so that's reflected on that. I mean, in general, correlation just is how two variables are related, but it does not really tell you where the data is actually coming from or the distribution of the errors. Okay, so although the p-value could be high and say that these two could be really highly correlated, it the errors actually matter, the residuals actually matter. Okay, so there are other important tests we can do. The last stat is a package collection, and also that has lots of statistical tests available, and outliers is another good collection that is that's useful for testing and detecting outliers. So you can perform this correlation test on 3 different variables. Actually, when it comes to correlation, there is also R squared, right? That can say how much is how they what's the goodness of fit. Okay, so we will see that. Linear regression. How many of you know about linear regression here? Okay, it's usually, I come from an engineering background, right? People talk about all the time about mathematics, and in engineering you see curve fitting, right? So you have a curve and you fit a data to it, and that's the similar concept as regression. And I was not really sure what is the essential difference between those two, right? But then after going through it in a deep, studying some of these things, the most of the things that they cover in engineering, they stop when they are trying to they are trying to minimize the errors, right? But they don't really put an emphasis on the distribution of errors and how the data comes from. So regression is a more detailed analysis of curve fitting, right? So it's in general, curve fitting just stops in one aspect of the data, right? I mean, everything would come under linear regression model. Even if you are fitting a quadratic curve, it is essentially linear regression that we are doing. We will see that in detail. Okay, so the aim of linear regression is to establish a linear relationship within parentheses in parameters. This is a very important, at least I found it to be an extremely important feature of linear regression, okay, between the predictor variables and the response variable. With such relationship, we can estimate the value of y when the predictors are known, right, when the x's are known. And we previously saw that there is a good correlation, right? So it suggests that there is a linear relationship between them, right? So we are trying to see that if there is a linear relationship. But first, let's assume that there is a linear relationship, and are we able to predict the cholesterol total when we have the values for LDL estimate, right? So that's the question that we are asking here. So to do that, what we will do is first try to collect these two variables from the data set, taking the Haynes data, selecting LDL estimate and cholesterol total, and I'm going to keep the analysis simple, okay, here. I'm just taking 30 random points for illustration purposes. I'm not going to do the entire linear regression on the entire data here, okay, so I'm just taking 30 points. And then I'm displaying it to see everything is okay. Now let's try to do some linear regression on this. But before fitting a linear model, right, there are key things that we need to do, right? The first is a scatter plot to see that how the variables are related, and that gives you a nice visual aspect of the relationship. The second is a box plot that will help to determine outliers, and it's very important to determine outliers because presence of certain outliers can really change and screw up certain statistics. Okay, and also the third thing is a density plot, which is actually, I would say, the density plot is not that important because the normality of random variables are not needed for regression, linear regression, right? But only the normality of the residuals are important. But we can do it for sanity check to see that the distributions are not utterly skewed, right? I mean, if there is a big skew, then it's going to be a problem. So what I'm going to do here is I'm going to take a plot and just plotting a scatter plot. Great, and I'm trying to smooth it. It's so nice. It looks like a line. And the second is this is kind of hinting to a linear relationship, right? And the second is we are trying to see the box plot, trying to see. But before plotting the box plot, right, I had an issue here because for plotting the box plot in the same ggplot, right, it was difficult because you have one variable here and the other variable here, and if you're trying to plot it, you're going to get it into two completely different plots, right? So I wanted to see it in one plot, and so I had to gather the variables here. Okay, so that's a small trick that I have to do here. So what I took the sample and then gathered these two so that I made the columns into rows. Okay, so instead of LDL estimate, and if you look at these, the previous, here you had the LDL estimate and cholesterol, right? I wanted to plot it in one plot to see that how these two varied, right? So I had to gather here, and you have it in the rows, right? Now you can plot these two variables, and then you can see that how they are vary, right? Otherwise, you will get it in two plots, and you don't, if you really cannot compare them, right, to see if there are outliers. So there aren't much outliers here except for one here and one here. So things seems to be nice. So we will study the density plot for these variables. So the density plot, similar. You don't need really the normality here, but except that here there is a little bit of a kurtosis, right? Skew. The distribution doesn't seem to be entirely skewed, right? So it's a reasonable assumption. So we may proceed with the linear fitting model, right? And in R, the function LM calls for the linear model. Okay, this takes into two main arguments, namely formula and the data. You can have several formulas. This is what it says is that this is a response variable and this is a predictor variable. So I'm just using only the LDL estimate and cholesterol here, and so we have this formula, and then we can print the linear model. Okay, so the linear model now tells you, if you just print out, it's going to give you two things. One is the intercept and the LDL estimate, right? The coefficient. So the model establishes a linear relationship between the LDL estimate and cholesterol. So the cholesterol in general can be written as intercept plus the coefficient of LDL estimate plus times the LDL estimate. So here it's 76.3 plus 1, right? So it's just so we can plot the relationship by making the size of the point to reflect the residuals, right? So this is what I'm doing here. So what I'm trying to do is I'm taking these points and doing some fancy plots to see that how far the errors are away from this, how far the residual are this, right? I mean, in general, it depends on the distribution of these points. Okay, so linear regression. So now we have the formula to predict the cholesterol. We can use it, but then we need to make sure the statistics are okay. So this can be used using the summary function. If you, almost all of these models, right, have something called summary function. So in the next class, we will see a more powerful form of modeling called the generalized linear models. But this is a basic linear model. Okay, so all of these methods, right, have a summary. And if you list out the summary, it's going to spit out something like this. You will have a residuals, and you have a coefficients, and for the coefficients we have the estimate and some of these values. Okay, so let's look into what these summary statistics tells us. Okay, the first is what you have a formula call. It's straightforward description of what's the call that we should. And the second is the residual, right? Residuals or the difference. You know what residual means? It's the residuals or the difference, right? So this is the residual that we have, right? This is the So they are the difference between the response values and what the model predicted, right, from the line. The residual sections, they break the summary into five summary points, right? It has this minimum, first quantile, median, third quantile, and maximum, right? And so it should be technically zero. That's one of the key assumptions for linear regression, is that the residual should be technically zero. In our case, it's closer to zero, right? I mean, and so it's I think 2.64 or something like that. Yeah, 2.64. The third is the coefficient. This section talks about the coefficients in the model, right? In a simple linear model, we have number of unknown coefficients that needs to be determined. At least there is only two. So the coefficient that is independent of the predictor variable is the intercept. Usually they call it as beta coefficients, beta naught, beta 1, etc., etc. The estimates of these coefficients come with statistics. So first is the coefficient estimate that gives you an estimated value of the coefficients, right? The estimate of the intercept means on an average, the difference between cholesterol and LDL is about 76.23. That's the average. And the LDL estimate coefficient gives a slope, right? And the second, you have the coefficient standard error. And this measures the average amount that the coefficient estimate vary from the actual average of our response variable, right? So we would want to see lower values relative to coefficients. And this can be used to construct confidence intervals. The third, you will see that t statistics. For all coefficients, you will see t statistics, and this is the estimated by the standard error. And so if the error is low, we want the t statistics to be high for a good fit. Okay, so these are sanity checks. And the next, you will have the probability of the values, the coefficients greater than t, right? It's a p-value that we get a t-value higher than an observed value. So it's a t-statistics, right? I mean, we can do a null hypothesis testing. So if it is low, then the coefficients are significant. And if it is high, the coefficients are not significant, right? In our case, they are extremely low. If you look at some of these t-values from our case, it's, I think, they are like, yeah, they are extremely low, suggesting that they are significant. And you have these codes. There are lots of coefficients. You can immediately look into these codes and see what are. And then you have the residual standard error. You have the multiple R squared and F statistics. Okay, so let's see what those are actually. The residual standard error is mathematically the sum of all errors by the degree of freedom. Okay, so the degree of freedom can, who knows what degree of freedom is? It's the number of observations minus the parameters that you use to fit the model, right? So it's that much of, I mean, you can think of it from a more linear algebra point of view, right? I mean, if there are going to be more equations than the unknowns, right? The unknowns are going to be less, especially if there is only 2 of them here and there are 10 equations, right? So you have to, when you have more equations than the unknowns, right? Is it, let's say that when you have more variables unknowns than the number of equations, then you can fit as much as you want, right? You can take the rest of the 0 and then make a constraint. But here it's an over constrained system, right? There is something called underdetermined system, overdetermined system, right? So in this case, this is an overdetermined system. And so the degree of freedom is the number of observations minus the number of parameters in roughly, okay? So we can before we look into this, and we can also, there are also other key summaries in here. One is called the standard squared error, SSE, that is given by y minus y hat squared. So where y hat is a fitted value of the observation, right? and then there is a sum of squared total. Okay, so that is the mean. So this is different. This is a y bar and this is y hat. Okay, so we have these several metrics for linear regression, and there is also something called as a mean squared error. Okay, so this is the sum of squared error divided by n minus q. Right, this is the number of observation, q is the number of coefficients. So once we have this multiple R squared statistics. So in our case, it's 0.94, meaning 94% of the variance is explained by the model. It explains how much of your variance can be explained, the multiple R squared, right? So if we add more predictor variables, R square will naturally increase, and adjusted R square takes into account the number of predicted variables. So there is another metric called adjusted R square, right? And there is also an F statistics, and F statistics, it's away from 1, it is better it is. I mean, because of the minimum, the mean squared error is in the denominator, right? So these statistics are for sanity checks. I mean, there are so much of assumptions that go into linear regression. Okay, so we can't really see something is linear and then think that something is linear and then say that's so there is something like this. If you have a, like, say for instance, you have a if you have something, it's still linear, right? Will the linear regression be okay with this? Points are here. Let's say that it's cool. Will the linear or regression be okay for this type of data? Yeah, so yeah, we will see that. But anyway, think about it. So if any of these assumptions are voided, linear regression may not be the best to fit the data, right? So we have to see, there are several assumptions on autocorrelation if there is a time series data and stuff like that, but we will see the main ones here. The first assumption is that the linearity is with respect to parameters and not exactly with respect to predictor variables. So this is still a linear regression. So if you're fitting a curve, it is still a linear regression. Okay, just because it is linear doesn't mean that it is linear in terms of variables, but it is linear in terms of parameters. Okay. The second assumption is the mean of the residual is theoretically 0, and practically it should be close to 0, right? The residual should be 0. Like, I mean, it's one of the key assumptions. The third, the residual should be normally distributed. So this is one of the key assumptions behind linear regression, and whether we are using maximum likelihood or ordinary least squares, the residual should be the error should be around the standard the normal curve. Right? So the data should be that's it. Note that even this kind of a funnel, right, still satisfies that. The errors will be normally distributed, right? So we can check the normal distribution. In our case, we have the residuals and we can see how far it is, right? I mean, we can draw quantile plot and we can do Shapiro's test and other tests, but we can also plot them, the density. So the blue line is the standard normal distribution and the red one is our residual, and we kind of have a normality here. So, right, and the fourth one is the homoscedasticity, right? So the funnel thing that satisfies all the condition. The residual is 0. The mean of the residual is 0, and it is normally distributed. But it invalidates one of these things, and this is very critical. On all the values should have the same variance irrespective of the values the random variable takes. Okay, so if you are going to have this, it should have the same variance. So in this case, this is violating that, right? This value, it should have the same standard deviation. So in this model, this cannot be, the linear regression cannot be applied in this case. Okay, there is something called global validation of linear models assumptions. So there is a good package GVLMA, okay, that can be used to check the assumptions. Okay, so install that package GVLMA, and then you can use that to see how far our assumptions are valid. Okay, it tests for several assumptions. So for instance, I checked in our case, it's all assumptions are all acceptable. You have the global statistics, you have the skewness, you have the kurtosis, you have the link function, heteros. Yeah, so all these things, right? I mean, you have all the model assumptions are acceptable. So that could be a good package to use. Okay, so as a homework, you need to fit a linear model to any of the variables of choice in Haynes or mimic data sets. Make a QQ plot for the residuals and check the assumptions. If the model fails, explain why it is the case. If the model succeeds, report the validity of the assumptions. Okay, so yeah, with that we will stop today. There are very good resources out there. I mean, there are so many resources out there for regression. It's, I mean, I try to cover which are all important, but the regression is a very big topic. On the linear regression, it's okay. I mean, there are so many conditions here, and also the one of the key assumption is that both are continuous variables. Both the predictor and the response variables are continuous. In some cases, most of the data sets, right, mimic 3 comes with categorical variables, right, and nominal variables. In those cases, what we can use logistic regression, and we will see how logistic regression is actually being implemented, or any of these regression, right, through maximum likelihood methods, and we will go through some of the gradient descent algorithms and stuff like that. So but don't fear. I mean, it's going to be a little bit technical, but it's more practical. I made it a point to illustrate with a data set rather than abstractly talking theory, right? I mean, so that's important to have in mind. I mean, so you are going to use, if you just follow my examples, right, you should be able to build your own project very easily. So that's the kind of emphasis that I'm placing on this course, that you should be able to do a very good project looking into some of the analysis methods that have been used. Okay, all right, so I'll stop with this today, and I'll let you work on some things, and I'll be here to take some questions or help you out with things if you want.